Okay, we have some questions here. Let's see. Today's review. Yes, today we're going to review. Somebody's asking, is there any way we can postpone the quiz? On the quiz today. So we're supposed to have a quiz today. Um, all right. Well, let's see. Yeah, it was already postponed. And I think we're gonna have the quiz today, all right? And then the exam is next. Will be next week as planned. All right. Okay. Any other questions? Okay. All right. So we're gonna review. We're gonna do a review, and then I'm gonna go over any homework questions that you had, and then hopefully we'll finish early, and guys can go over and do the quiz. Okay. Oh, the quiz is today. Okay, the quiz is today, and our second exam is going to be next week. Okay. All right. So let's go over this. All right, give me 1 second here. Okay. All right, so we're going to go over everything from chapter 2, including 2.3 and 2.4. All right. So chapter 2, review. Okay. We're going to start with 2.1, which deals with sets. Okay. All right. So sets. So from this chapter, make sure you know all the definitions, the different definitions we discussed. Okay, and I'll go over most of them now. All right, so we discussed sets. We just talked about what a set is. All right, we talked about what it means to be an element of a set. Right. We talked about subsets of a set. Okay. All right. We talked about proper subsets. All right. And we talked about equality of sets. Okay. All right. So for subsets and proper subsets, just to review the difference, right? A is a subset of B, means that A has less elements than B, where all the elements from A are in B, or A is equal to B. Okay. So when I use this symbol, that allows for equality. So this means either A is equal to B or A is a subset of B. All right. When I talk about proper subsets, that means A is a subset of B and A is not equal to B. Okay. All right, think of it like less than or equal to, like the less than or equal to sign. Okay, and two sets are equal if they have the same elements, meaning any element that's in one is also in the other. Okay, and if we do not care about repetition. Remember that. So if A has a certain element repeated, we only count it once. Okay. We also talked about cardinality. The cardinality of a set S. All right. That tells us how many distinct elements are in the set S, okay, as well as the power set of S, right? P of S. That's the set of all subsets of S, okay. And remember that if the cardinality of S equals n, the cardinality of its power set is 2 to the n. Okay. We also discussed the empty set or the null set. Okay, we said the empty set is a subset of every set S, and we also said S is a subset of itself. Okay. We also talked about Cartesian products. All right, A times B. All right, that's a set of n tuples or two tuples where the first element comes from A, the second element from B. Okay, or in other words, it's a set of ordered pairs. All right. And we talked about truth sets. So remember, a truth set is just the set of elements in the domain that makes a quantified statement true. Okay. All right. Okay. We discussed different ways to list the elements of a set, right? We talked about set builder notation and the roster method. Okay. Either way, you should know both ways of listing a set. Either way you list a set is fine. Okay. And so let me put that down as well, roster method and set builder notation. All right, in the roster method, remember, you just basically list the elements of the set. With set builder notation, you sort of describe the elements that are in the set. Okay. All right, so that was 2.1. Any other questions on 2.1? All right, let's move on to 2.2, which we dealt with set operations. Okay. So we discussed a few different operations that you can perform with sets. We talked about the union of two or more sets, the intersection of two sets. So the union of two sets is the set that contains all elements that are in both sets. So it's basically just combining the two sets into one big set. The intersection of A and B is the set of those elements that A and B have in common. All right, so it's those elements that they share. We also talked about difference of two sets, A minus B. Okay, that's the set of all elements that are in A but not in B. So it's everything that's in A, and from A we remove the intersection, those elements that A shares with B. Okay. All right, and if you have a universal set U, which is sort of like our domain, then we can define something called A's complement, which is just U minus A. Okay, that's everything in the universal set that's not in A. So complement. Okay. And we also discussed generalized unions and intersections. Right, that's when you have the union or the intersection of many sets. Okay, either many sets or even infinite sets, right? So we discussed the union from I equals 1 to n of A sub I, right? That's A1, union A2, union dot, 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 all the way up to A sub n. And we also discussed this with an infinite number of sets. So this would be A1, union A2, union A3, dot, dot, dot. That would continue forever. Okay. And the same thing for intersection. So the intersection from I equals 1 to n of A sub I, that's A1, the intersection A2, dot, 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 all the way up to AN. And then we could have the same thing from 1 to infinity. Oh. Okay. Et cetera, et cetera. Okay, so those were the set operations we discussed. Any questions on those? Sure. All right, so let me scroll back for a moment here. Okay. A universal set U is sort of like a domain. Okay, it tells us what our elements are allowed to be. Okay, so for example, let's say I say my universal set is the set of integers. So then every set that I make has to consist of integers. Okay, I can't use anything else, right? So A bar, the complement of A, would be everything in my universal set that's not in A. Okay, so for example, let's say my universal set was a set of integers, and let's say A was the set of even integers. So A bar would be U minus A, so it's everything else, so it would be the odd integers. Okay. 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 All right. Any other questions on 2.2? All right, let's move on to through 2.3, functions. Oh, generalized, yeah. So generalized is just where I have a union of multiple sets, all right? Or an intersection of multiple sets. So a generalized union is where I have a union of several sets, okay? So that would just be where I'm combining them all into one big set, okay? And a generalized intersection is going to be the intersection of all the sets. So it will consist of only those elements that appear in every single set. Okay, so the generalized intersection would be just those elements that all the sets have in common. Right? Yeah, yes, sir. I think that looks right. Yes. Okay. A minus B. So A minus B, the difference of A and B, A minus B is, again, it's the elements of everything that's in A, but not in B. Okay, so in other words, I'm removing from the set A anything that it shares with the set B. Yeah, exactly. Okay. To 2.1. All right. Was there something specific in 2.1 you wanted to see? Oh, okay. Somebody's going to upload it for you. Okay, great. Thank you. Okay, so functions. All right. So first of all, definition of a function. What a function is and what a function is not. Okay. So remember, for something to be a function, all right, keep in mind two things. All right. Number one, every element in the domain has to be a pre-image. Okay, it has to be assigned something from the codomain. Okay. If there are elements in the domain that are not assigned anything in the codomain, it's not a function. That's one. Two, okay, right? So in other words, if I've got okay, let's say I got something like this. Oh, here, let me write it this way. Okay. Let's say I've got something like this. Okay, this is not a function. Why not? Because there's an element in my domain that's not assigned anything from the codomain. So that would not be a function. Another example of something that's not a function is this. Okay, that would not be a function either. Why not? Because here I have an element in A that's assigned more than one element in B, right? So if we were looking at it like this, let's say I had something like f of x equals plus or minus the square root of x. That's not a function, right? Because for a single value of x, I get two y values, plus or minus the square root of x. So this is not a function. Okay. And so to here, this is not a function because A2 is not assigned anything. A2 is not a preimage. Okay. So what would be an example of that? Let's say I gave you a function f from the set of real numbers to the set of real numbers. Okay, and I told you f of x equals 1 over x. Okay. This is not a function because why not? Because my domain is the set of real numbers. Okay, 0 is a real number, but I can't plug in 0 into this thing. Okay, so for this thing to be a function, I would have to take 0 out of the domain. Okay, by keeping 0 in the domain, this thing is not a function. Right, 1 over 0 is undefined. Right? So the only way that this thing would be a function would be for me to remove 0 from the domain. Okay, but by including 0 in the domain, I have an element that is not a pre-image. It's not assigned value, so it's not a function. Okay. So definition of a function, what a function is and what it is not. Know all the definitions from this section. So domain, codomain, know the difference between the codomain and the range, right? The range is a subset of the codomain. The range is the set of all elements that are images, right? So make sure you know what pre-image and images are. Pre-image, image, right? So remember, pre-images are those elements in the domain that are assigned to the elements in the codomain, and the images are the elements in the codomain that are assigned to elements in the domain. Okay. Right, so if I tell you f of a equals b, then b is the image, a is the pre-image. Okay. All right. No, you don't have to be able to write out the definitions. Okay. The difference between range and codomain again. All right. So again, the codomain can be whatever you want. It's any set you want it to be. The range will be a subset of the codomain. The range will be those elements that are assigned to something from A. All right. Or we'll get to onto and one-to-one in a moment. All right. All right. All right. So for example, if you have this, okay, your codomain is B1 comma B2. Your range would be B1. Okay. All right. All right. So we discussed one-to-one and onto. Okay. What does it mean to be one-to-one and what does it mean to be onto, right? So remember, a function is one-to-one. Okay. If and only if every element in my range has exactly one pre-image. Okay, so meaning I can never have the same y value occurring more than once. Okay? I cannot have a repeating y value with different x values. Okay, onto, what does onto mean? Onto means that every element in my codomain is also in the range, meaning every element in the codomain has some pre-image. So for every element in my codomain, I can plug in some x value to get that number. Okay. All right. All right. So how do we tell if a function is onto or not? Well, a function will not be onto. There's no formula. You just sort of have to work it out. Basically, you have to look at the codomain and ask yourself, is there some number in the codomain that this function can never be equal to? Is there some value I can pick for y that my function cannot be equal to? Okay. So, and again, that also depends on the domain. All right. So is there some x value that I can find in my domain that will give me this y value? Okay. If I cannot find an x value in the domain to give me a y value from the codomain, it's not onto. All right. Yeah, we could do an example. Okay. The most basic example that we did was, let's say, y equals x squared, or f of x equals x squared. Okay, let's say this is a function from the set of real numbers to the set of real numbers. Okay. Here's my domain and codomain. The codomain is the set of real numbers. So are there real numbers, are there elements from my codomain that my function cannot be equal to? Okay. So the answer is yes. For example, -1 is a real number. Can my function be equal to -1? And the answer is no, because what would x have to be? X would have to be the square root of -1, which is not a real number. So, right, the square root of -1 is not a number in my domain. So this thing can never equal to -1 with the given domain. So x squared cannot equal -1, so it's not onto. Okay, to be onto, it has to be able, my function f of x has to be able to be equal to every single number in the codomain. So you got to just sort of look at their codomain and think, can I find some number that this thing won't be equal to? The horizontal line test only will work for one-to-one functions to test if something is one-to-one or not. Okay. Okay. And your domain and codomain, by the way, do not have to be the same thing. They can be different things. Okay. All right. Any other questions on that? Okay. Surjective means onto, right? That's the same thing as onto. I don't know what you mean by some domains can equal multiple codomains. I'm sorry. Can you use the horizontal line test for one-to-one functions on the exam? Yeah, that's sure. That's fine. Yeah, I'm sorry, Ajman. I'm not sure what you mean by domains equal multiple codomains. To be a one-to-one function, if you pass the horizontal line test if you pass the vertical line test, then it's a function. Okay. If you pass the horizontal line test, then it's one-to-one. Okay, but that doesn't tell you if it's onto or not. Okay. The Cartesian product. The Cartesian product really is. Oh, I think I know what you're asking. How do you do the Cartesian product by using onto? Do you mean how do you check if a function is onto where your domain uses a Cartesian product, like some of the homework problems? Is that what you mean? Okay. So again, you just sort of have to work it out. All right. So like, for example, let me do a quick example here. All right. Let me do an example here. Let's say you're given the following. F is a function from the Cartesian product z times z to z. So this means that I'm plugging in two numbers, m and n, where m and n are both integers, and I get out some integer. Okay. Let me call it z. Okay. So let's say I tell you your function is f of m comma n equals m plus n. Is this onto? Okay. All right. So in other words, my codomain now is the set of integers. Okay. So is there an integer that my function cannot be equal to, or can my function here be equal to every integer? Right. Well, the answer is that this thing is onto. Right. Because pick any integer you want. All right. I can let m plus n. Let's call it z. Pick any integer you want, z. Okay, so z is any random integer. I can make m plus n equal to z. How? Just let m equal z and n equals 0. Okay. Then m plus n will be z plus 0, which would be z. So pick any integer z you want from the codomain. I can make my function equal to it. So it would be onto. Oh, don't worry. Welcome. Okay, I hope your system is working fine now. Yeah, sure. So let me explain that again. Okay. So this function, f of m comma n equals m plus n, is onto, all right, where my domain is z times z, meaning m and n. This tells me that m and n both have to be integers, and my codomain is also the set of integers. Okay. It's onto. Why? Because m plus n I can make equal to any integer I want it to be. Okay. For example, let's say I pick 5, right? Can I m plus n equal to 5? Yes, just make m 5 and n 0. There's more than one way I could do it, by the way. All right, that's fine. So it wouldn't be necessarily one-to-one, but it's onto. All right. So m equals 5, n equals 0. Let's say I want it to be equal to 0. How do I make it equal to 0? Make m 0 and make n 0. Let's say I want m plus n to equal -1. Just make m -1 and 0. Okay, and so on and so forth. So it's on to. No, that's just one example of how I could I'm showing it's on to. It's not the only way of doing it. Okay. All right. Okay, so that's on to and 1-to-1. Yeah. Yeah, for any, as long as I can, m plus n can equal to any integer z. Okay, then it's on to in this example. Okay. Let's see. When would it not be onto? So let's take the same domain and codomain, and let's say I gave you f of m comma n equals m squared plus n squared. Okay, this would not be onto. Same domain and codomain from before. This would not be onto. Why not? Let's say I want to pick from my codomain. Let me pick an integer. Let's say I pick 3. Okay. Can m squared plus n squared equal 3, where m and n both have to be integers? No, right? Like, for example, let's say I make m and n both 1. I would get 1 squared plus 1 squared, which would be 2. Right? That's not equal to 3. Right? Let's say I make this 2 and this 1. I would get 5, again, not 3. Okay. And so I really have no options. I've got nothing in between. I go from 2 straight to 5. Okay, so this thing can equal to 3. Or if I did 2 squared plus 0 squared, that would be 4. Again, it's still not equal to 3. So there's no way I can get this equal to 3. This m squared plus n squared, where m and n both have to be integers, can never be equal to 3. But 3 is an element in my codomain. 3 is an integer, so it's not onto. Okay. Right, or a negative number. Right, negative number would work too. Okay. All right, it can't be negative either. Okay. All right. So that was onto and 1-to-1. Next was a bijection, right? Remember, a bijection is just a function that is both 1-to-1 and onto. Okay. Okay. So bijection is a function that is both 1-to-1 and onto. All right. 1-to-1 and onto. All right. Okay, we also discussed in this section inverse functions, right? F inverse of x. Remember, f inverse of x is the inverse of f of x. So f inverse of x equals y if f of y equals x. All right. And we also discussed the composition of functions. Okay, so f of g of x is f of g of x. Okay. Right. And remember, we also said that f of g of x composition does not commute, so that is not going to be equal to g of f of x. Okay. Okay. The horizontal line test again is if you draw the graph of your function and you can draw a horizontal line that intersects the graph more than once, then it fails the horizontal line test. Okay, it's not 1-to-1. When we use inverse in composition, okay, so for inverse in composition, the composition of a function with its inverse is just x. Okay, so that's one way you could use it. And I could also ask you, I could give you f of x and g of x and ask you what is their composition. So I could say f of x equals x squared, g of x equals 3x. What is f of g of x? All right, so that would be f of 3x, which would be 3x squared, right? I'm plugging in 3x into x for f of x. So you would get 3x squared, which is 9x squared. Okay, and g of f of x would be g of x squared, which would be 3 times, and I replace x with x squared, so I would just get 3x squared. Inverse. Oh, well, here, let me give you another example for the inverse. Okay, let's say I tell you I have a function f of x, okay, and I tell you f of 8 equals 3. So if I have an inverse function, f inverse, then f inverse of 3 has to equal 8. So an inverse function basically just does the reverse, or the inverse of what the function f does. Okay, so if f of 9 equals 2, then you know f inverse of 2 equals 9. Okay, great. And also, just something I think I've pointed out before, f inverse of x is not equal to 1 over f of x. That's not what the -1 means. Okay. Okay. All right. Okay. So that was inverse in composition of 2 or more functions. The final thing really to know from this chapter is the floor and the ceiling functions. Right. The floor function is the largest integer less than or equal to x, right? So remember, we're always rounding down. And the ceiling floor function, that's the smallest integer greater than or equal to x. So remember, we're always rounding up to the closest integer. Okay. All right, so that was 2.3. All right. Next is 2.4. Okay. 2.4 dealt with sequences and summations. All right, so we discussed sequences. We talked about geometric and arithmetic progressions, which are special types of sequences. For a geometric progression, in the general form of a geometric progression will be a sub n equals a times r to the power of n, where a is the initial term, r is the common ratio. For an arithmetic progression, it would be a sub n equals a plus n times d. A is the initial term, d is the common ratio, common difference. Okay. We also discussed recurrence relations. Right, that's when a sequence is defined by one or more of its previous terms. Right? And we talked about solutions to recurrence relations. So remember, a solution to a recurrence relation is basically just an explicit formula or closed formula that gives me the same sequence as the recurrence relation. Okay. We talked about the Fibonacci sequence. All right. Right, and that was really it for sequences. We discussed summations and double summations. Okay, and we also discussed the some summation formulas. Okay, so we discussed the summation formula for geometric progressions, and then I gave you 3 other ones that I said you should know, right? The sum from k equals 1 to n of k squared, and of k cubed. Okay. All right, let me see questions here. Do we have to know factorial functions? No, non-factorial functions. Just know what a factorial is. n starts from 0 for those formulas, yes. Except, well, for the geometric progression, yes. For the others, it starts from 1. Okay. Yeah, the floor function rounds down and the ceiling function rounds up. That is correct. For recurrence relations, so for recurrence relations, I'm going to have to, if I ask you what is the, like, say, the next term of the sequence or something like that, and I give you a recurrence relation, I have to give you some initial term to tell you what A0 is equal to, or what A0 and A1 are equal to, or something like that. Okay. How do you change the base index for what? For summation? I'm not going to ask you on it. I wouldn't ask you on a test to change the index. All right. But again, if you want to change the index, then whatever you decrease it by or increase it by, then in the sequence itself, you have to do the opposite. So if you decrease your index by 1, by the terms of the sequence, you have to increase the index by 1. I need to tell you where n starts from. So I would have to tell you if it starts from 0 or from 1. Okay. Do we have to do proofs? No, not for chapter 2. When will we change the index? There are times when it's convenient. We're not going to do it here, though. Okay. All right. A double summation example? Oh, yeah, sure. Okay. Okay, let's do one. Okay, let's see here. Let's say I give you the sum from I equals 1 to 2 of the sum from j equals 1 to 3 of I plus j. Okay, so you start by doing the inner sum, which is the one on the right, the j. So sum from I equals 1 to 2 of. So I'm doing this one first. Okay, I start by plugging in the numbers for j. So if I plug in 1 for j, I'm going to get I plus 1. Then I plug in 2 for j. I get I plus 2. Then 3 for j. That's I plus 3. Okay, so summing all of that up, I get, that's 3i plus 6. All right, next plug in the numbers for I. So I'm going to get 3 times 1 plus 6 plus 3 times 2 plus 6. All right, that's 3 plus 6 plus 6 plus 6, which is 21. Right, the inner one is the one on the right, okay? Okay. All right, I believe that is it for chapter 2, section 2.4. Any other questions on 2.4? Yes. Don't we need to solve for the outer as well? Yes, I did that at the end. Okay. Okay. Yeah. Okay. Right, so I plugged in the values for I at the end, and then I got my final answer, which was 21. Okay. All right, let's move on to 2.6 now. That's the final section, and then after that, we'll be done with our review. 2.6, we discussed matrices. Okay. You should know, the main thing you need to know is how to do matrix arithmetic. So adding matrices and multiplying matrices. You should know the definitions I gave you last time too. Right, for the identity matrix, for a symmetric matrix, for the transpose of a matrix. But the main thing is going to be adding and multiplying matrices. Okay, so also know transpose, identity, square, symmetric. Okay, those were some definitions we discussed last time. Okay. All right. All right. So there's one homework problem that I do want to go over from 2.6 with you guys. 2.6, question number 5. Okay. So I want to do that, and then with that, we'll finish. Okay, so 2.5 asks you the following. Excuse me, 2.6, question 5 asks you to do the following. Find a matrix A such that the product of two matrices, where the first matrix is 2, 3, 1, 4, times some matrix A, so A here represents a matrix, equals the matrix 3, 0, 1, 2. Okay, so what is the matrix A? If the product of the A and this other matrix equals to the given matrix. Okay, all right. So in order to solve this, the first thing you need to ask yourself is, what size is the matrix A? Yeah, okay. If this first matrix here is a 2 by 2 and the resulting matrix is a 2 by 2, well, I know in order to multiply them, the number of rows of A has to equal the number of columns of the first matrix. So it's got to be 2 by something, okay? And I also know that this number here that I'm circling now came from the number of columns here of this matrix came from the number of columns of A. So if this number is 2, A had to have 2 columns. Okay, so this number here gives me the rows of A. This number here, well, this number here gives me the columns of A, the number of columns. So A has to be a 2 by 2. Okay, so I'm going to rewrite this as 2, 3, 1, 4 times A, B, C, D. I'll make up 4 letters there, equals 3, 0, 1, 2. Okay, so A has to be a 2 by 2 matrix, and that means it's got 4 entries, right? 2 times 2 is 4. And I'm going to call them A, B, C, D. Okay. All right. So now, how do we figure out what A, B, C, and D are? By multiplying. Okay. So if I multiply, I know that the first row of of my first matrix, excuse me, times the first column, first row times first column. When I multiply and add, it has to equal to 3. Okay, so I know that 2 times A plus 3 times C has to equal to 3. All right, and if I do the first row times the second column, so 2, 3 times BD, that's going to have to equal to 0. So 2B plus 3D equals 0. Okay. All right, next, second row, first column. When I multiply, I get 1 times A is A, plus 4 times C. That has to equal to the second row, first column here, which is 1. So that's got to equal 1. Okay. And final product, second row, second column. 1 times B is B, plus 4 times D is 4D. That's going to be second row, second column. Second row, second column is 2. So B plus 4D has to equal 2. Okay. So by multiplying all of these things, I get here a system of equations. I get 2 systems of 2 equations. Okay. So to find A, B, C, and D, I just now have to solve this system of linear equations. All right. So you got to remember how to do that. You solve the system of linear equations, and you'll get the A, B, C, and D, and you plug them in. All right. Okay, so you can solve these things any way that you remember how to do it, any way you like is fine. All right. I'm going to do it as follows. Yeah. Yeah, you're getting fractions. You should be getting fractions. Yeah. Yeah, you'll get fractions sometimes. That's fine. Okay. All right. So what I'm going to do to solve this is I'm going to multiply this one here by -2. This way I get 2A plus 3C equals 3, and then I get -2A minus 8C equals -2. Okay. Now when I add them up, 2A minus 2A will cancel. So I'm left with 3C minus 8C, -5C. 3 minus 2 is 1. So C equals -1/5. Okay. You plug that back in to one of the two equations to get what a is equal to. Okay. Okay. All right, so let's say I plug that into a plus 4c. So a plus 4 times negative 1/5 equals 1. So a minus 4 over 5 equals 1. So plus 4 over 5 plus 4 over 5. A equals 1 plus 4 over 5, which is 5 over 5 plus 4 over 5. So a is 9 over 5. Okay, so that's a, and that's c. All right. I'm going to scroll up for just a moment. I'm going to come back down in a minute. We're now going to do the same thing for b and d. So here I'm going to multiply b by -2. I get 2b plus 3d equals 0. Negative 2b minus 8d equals -4. Now when I add, the b's will cancel. I'm left with 3d minus 8d is -5d equals -4. Divide by -5. D equals 4 over 5. So that gives me D. Plugging that back in, I get B plus 4 times 4 over 5 equals 2. All right. So B plus 16 over 5 equals 2. B equals 2 minus 16 over 5. So B is 10 over 5 minus 16 over 5, which is -6 over 5. So I've got A, B, C, and D, and I'm done. Okay, the matrix A, which is A, B, C, D, equals A is 9 over 5. B is -6 over 5. C is -1 over 5. D is 4 over 5. What happened here? Okay, there we go. Okay, and that would be our answer. Okay, this is the matrix A. Yes, this I'll scroll up. Sure. To what part? To here? Is that good? Okay. All right, let me scroll down again for just a minute. I want to just show everybody one more thing. One more thing that you don't have to know this, just as a side point. With matrices, I can factor out common factors. So if you notice, every term in this matrix has a common factor of 1 over 5. So you could factor that out. You could write this as 1 over 5 times 9, -6, -1, 4. Okay, it's the same thing. All right, you don't have to know that. I just wanted to point that out. (2.6), number 19. Let me take a look. No. That's basically kind of like a proof. I'm not going to ask you to do a proof for this exam. Okay. Our next exam we'll get more into proofs again, but not for this exam. Okay. All right. Any other questions about any of the other problems or anything else about your exam? All right. So again, the exam is going to be Monday during class. A similar format. 2.6 is just matrices. Yeah. All right. It'll be similar format to the previous exam. Okay. It's roughly the same number of questions as the previous exam, more or less. Okay. Very similar format. Okay. All right. With that, we will end here for today. If nobody has any other questions. Yeah, there'll be a mix of multiple choice and short answer. Very, very similar format to the previous exam. Okay. All right, so let's end here for today, and you can use the rest of the class time to go do the quiz. The quiz is 10 questions. It's a mix of different types of questions, some multiple choice, some true and false, some you have to fill in the answer. Okay. So you can go to Blackboard now. I'm going to make sure it's available. Give me one moment. Give me a minute here. Okay, it should be available now, so you should be able to see it. Okay. All right. All right. If for any reason, do the exam quiz. Yeah, quiz 3. All right. If for any reason it says your submission is late or something like that, don't worry about it. I'll submit it for you. It's fine. Okay. I mean, I'll fix it for you. All right. So don't worry about if it says your submission is late. Just work on it and answer the questions. And good luck, everybody. All right. I'll be here if you have any questions. Okay. I believe it will end automatically after 20 minutes. I believe that's how I set it up. All right.